How does the monoclinic arrangement in polycrystalline naphtha P2O7 influence its electrochemical performance? And what role do the specific structural motifs play in determining the material's conductivity and stability? In what manner do the charge and discharge curves of naphtha P2O7 illustrate the underlying electrochemical processes? And what can be inferred about the material's capacity retention, voltage profile, and cycling behavior from these curves? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the observed rate performance of naphtha P2O7 contribute to our understanding of its potential application in battery technologies? And which aspects of its crystal structure might be directly affecting its behavior under different current densities? What experimental or analytical techniques are employed to differentiate between the I and 2 naphtha P2O7 structures? And how do these techniques help in correlating the structural differences with the overall electrochemical performance? In what ways might further variations in the synthesis parameters or processing methods impact the formation of these distinct monoclinic phases? And how could such modifications potentially optimize both the charge-discharge characteristics and the rate performance of naphtha P2O7? How do these interconnected questions not only enhance our understanding of the structure-function relationship in this material, but also pave the way for future investigations into designing advanced cathode materials for next-generation sodium-ion batteries? How might the incorporation of transition metal compounds such as Ni, Co, and others influence the chemical and electrochemical properties of these materials? And in what ways could these elements modify the overall performance of fluorophosphate compounds? What exactly are the common features shared by this class of materials that allow them to compensate for the inherently low working voltage and limited conductivity observed in fluorophosphate systems? And how do these features manifest at the atomic or structural level? How does the integration of various transition metals into polyanion compounds with sulfate groups potentially enhance the electronic conductivity and improve the working potential when compared with pure fluorophosphate compounds? And why might the sulfate group play a critical role in this improvement? In what ways could substituting different transition metals lead to a controlled tuning of the electrochemical properties, and how might these adjustments be optimized for specific battery applications? What are the theoretical principles and experimental observations that support the idea that transition metal-based sulfate polyanion compounds will become increasingly important for future energy storage solutions? And how do these findings set the stage for further investigations into overcoming current performance limitations? What?